Consider the following Canada Math Olympiad problem from this year. We have two positive integers a and b, and we say that they are prime related if they satisfy one of these two relations. So for example, say 2 and 6. Yes, they are prime related because all you do is you divide the larger one by the smaller one, and if it's a prime, yes, they are prime related basically. Well, 36 and 12 are two prime related numbers again, or 2 and 4, they are prime related. Two numbers that are not prime related, well, 2 and 8 for instance, they are not prime related because 4 is not a prime. Awesome. So we would like to find all positive integers n such that n has at least 3 divisors, meaning that it can't be prime. So let's write that down. N not a prime, not a prime. As you know, primes have only 2 divisors, 1 and the number itself. And all divisors can be arranged without repetition in a circle, okay, so that any 2 adjacent divisors are prime related. So we create a circle, and all the divisors of our number, we try to fit into that circle, right? Okay, so that's weird. So if the number has, if your number is n and pretend that it has d of n divisors, then all these divisors would be on that circle in such a way that any 2 adjacent entries, divisors, for instance, these 2 are adjacent, they should be related, they should be prime related, just in the sense that we defined. So for instance, when I first read the problem, one of the first things that I start thinking was 1. So 1 should be a neighbor. The 2 neighbors of 1 should themselves be primes. Obviously the 2 neighbors would be larger than 1 itself, and so 1 would be in that description. So whatever number you are putting next to, so a is equal to p times 1, which is just p. So the 2 neighbors of 1 better be primes. Prime. And well, if you will have 2 primes, obviously 2 distinct primes, because you cannot repeat without repetition, then the number itself should have to have at least 2 primes in it. Does that make sense? So you have a prime on its left and on its right, and so boom. So therefore, first of all, the number n cannot be a power of a prime. Does that make sense? So n is not a prime, but it's also not a power of a prime. Just to give you an example, for instance, 4, the number 4, d of 4 is 3. So the divisors of 4 are 1, 2, and 4. Indeed, if you try to place them, there's actually a unique way to place it, so you cannot do anything. But this is not a good configuration. Yes, 1 and 2, they are prime related. They are neighbors and they are prime related. 2 and 4, they are neighbors, they are prime related. 4 divided by 2 is 2. But 4 and 1, they are not prime related. So, alright, so therefore, at least, well, still, we don't know what n can be, but we know for sure that n cannot be a prime power. A prime or power of a prime. Oh my gosh, terrible handwriting. A prime power. Okay, there you go. So n not equal to p to the power k, for instance, something like that, where p is prime, p prime. Awesome. So let's test it then. All right. Let's test a few numbers just to check. So one of the first numbers that I was thinking about was 6. So 6 has 4 divisors. So divisors of 6 are 1, 2, 3, and 6. So therefore, let's draw a tiny circle because we don't have too many divisors. Obviously, the critical beginning point should be 1. And 1 should be neighbor, the neighbors of 1 better be 2 primes, like we said earlier. So this neighbor and that neighbor, they have to be prime, and we already used 1. So there's only 2 prime numbers, right? 6 is not a prime. So therefore, I have to put a 2 and a 3 next to 1. And so therefore, there's only 1 spot left for 6. Let's just confirm that these two are prime related. Of course, 6 over 2 is 3. It's prime related. 6 over 3 is 2. Again, prime related. Good. So therefore, 6 is one of the numbers. And the reason, like, obviously 6 is a nice number is because it has 2 primes in it, 2 and 3. So let's think of another example which have, I wonder if all the numbers which have 2 primes in them work. For instance, we can just increase the exponent of one of them. So 2 squared times 3. 12 is a nice number. So the divisors of 12, well, obviously 12 has 3 times 2, 6 divisors. 1, 2, 3, 4, 6, 12. Let's go ahead and try to see if we can fit them on a circle, slightly larger circle with 6 marks on it. And like I said, 1 is on the central stage. Again, because we have only 2 primes, the neighbors of 1 has got to be 2 and 3. And now let's proceed. So I need to put next to 2 a number. It can be, so far we used 1, 2, 3. I can put 4, yes. I can put 6, yes. 6 over 2 is 3, it works. 4 over 2 is 2, it works. I cannot put 12. When I investigate what I can put next to 3, obviously again I cannot put 12. 12 over 3 is 4, it's not a prime. 6 over 3 is 2, is a prime. 4 is not. So therefore, next to 3 there's only one option. So instead of thinking about what to put next to 2, I can definitely, there's only one choice for here, it says 6. But again, because 12 cannot be here, so 12 has got to be here, and this guy's that works. So 1 and 2 are prime related, as is 1 and 3. 2 and 4 are prime related. 4 over 2 is 2. 12 over 4 is 3, prime related. 12 over 6 is 2, again a prime related. 6 and 3, 2, prime related. 3 and 1, prime related. That works. So far, we're on a good run. It seems like anytime you have, if our number is divisible by 2 distinct primes, it seems good so far. Let's test one more. Let's increase the powers one more time. 2 squared times 3 squared. Now this one will have 9 divisors. So d of, what's that? 36 is it? Okay, so the divisors are 1, 2, 3, 4 divides it. 5 does not. 6, what, 9, and then we go back. Wait a second, how many divisors does this guy have? Oh, 9 only, sorry for that. Yeah, so 9 times 4 is 36, so therefore 3 times 12, 2 times 18, and finally 36 itself. Okay, so let's go ahead and draw our circle. We have to put 9 markings on it. Okay, there you go. All right, so we have our 1 at the central stage. Again, because I only have 2 primes, I have to put 2 and 3 next to it. And now let's speculate what can come next. So far we used 1, 2, 3. What can come next to 2 and what cannot come next to 3? And let's see if we can reduce the casework. Well, obviously 4 cannot go next to 3 for sure, so this guy cannot be 4, so this guy can be a 4. It can be a 6 also. It can't be 9, so next to 2. So far it can be a 4 or a 6. It can't be 9, it can be 12. No, 12 over 2 is 6, it doesn't work. 18 over 2, 9 doesn't work. 36 over 2, 18 doesn't work. So this guy is on either a 4 or a 6 next to it. So we can either go that direction, or let's check the other direction. So this guy can be a 6. It can be a 9. 12 over 3 is 4, won't work. 18 over 3 is 6, won't work. 36 over 3 is 12, won't work. Okay, so 6 can go in either one. 4 only here. If it's 9, only here. So, well, we are indifferent. So let's try doing a casework. Okay, so we don't have any advantage. 4 or 6 here. Let's go with 4. If that case fails, then we will try the 6. So after we put a 4 here, so 4 is gone. The next number, well, there's only one option really, and it's the 12. I have to put a 12 here. Do you guys see why? Because 36 over 4 is a 9. It's not a prime. 18 is not divisible by 4. 9 is not divisible by, and 6 is not divisible by 4 either. So this guy has got to be a 12. Remember, next to 3, I have to reserve either a 6 or a 9. So I cannot use both 6 and 9 on these 3 squares, right? I have to either reserve a 6 or a 9 for that spot. Okay, next, because I used 12, intuitively I kind of feel like I have to slip in the 36 right now, but I can actually either put 36 or a 9. Both of them work, and sorry, I meant to say 6. 36 or 6. Let's try 36 first, and then we can try 6 as well. So if I try 36, well, these two are prime related, 12 and 36. So we use 36 as well. Then maybe I can put an 18 here. So 18 is good. And then I can put a 9. I can put either a 9 or a 6. Yeah, 9, and then there's only a 6 left. So 9 works. Hey, this one does not work. Haha. Awesome. So you can have a look at the other remaining cases, but it will be clear after a while that 36 won't work. So 12 works, check. 6 works, check. So, but 36 didn't work. Why did it not work? What's wrong with 36? So that's a question that might you guys can start thinking about, right? Well, we can have quite a few observations, but one thing that happened, so there might be anything that might have gone wrong, right? But one thing that's happening between when you go from one vertex to the next along that circle, you just realize that the two numbers are related by a single prime. So therefore, in the prime representation of any given two adjacent numbers, they differ by a prime, right? So therefore, yeah, so that's kind of the main idea going on here in general. But as it relates to this case of 36, it turns out that the reason that 36 actually didn't work is because 36 is a prime. Sorry, I meant to say it's a square. 36 is a square, and what's wrong with a square? Well, squares have an odd number of divisors. Like we did in this list, we just realized that there are 9 divisors, and versus 12 and 6, so these are not perfect squares, and they have an even number of divisors. So that's kind of the crux move. So when you have an odd number of divisors, what's wrong is the following. And obviously this proof is based on AOPS user in control, I guess. Here is the main idea, which makes a lot of sense once you start thinking about this problem. You start from 1, and you go, in total we need to check 9 relationships, right? So because there are 9 points, there are 9 neighborly relationship. So what happens as we start from 1, we go to 2. It turns out that there is I don't want to call it an invariant. I don't think it's an invariant. It is kind of like a monovariant, but it's not even a monovariant. So what happens is each time the number of the sum, I should say, the sum of the powers in the prime representation of the numbers as you go from one vertex to the next increases or decreases by 1. For instance, here it went up by 1, up by 1, up by 1 because you multiplied it by 3, up by 1, down by 1, down by 1, nothing, the chain broke, down by 1, down by 1. But because we have 9 gaps, we start at 1 And we should have an even number of gaps, right? So an even number of prime related relationships, so an even number of adjacent vertices, so that, for instance, so that you go back to the same number, right? So the sum of the exponents in the prime representation shouldn't change because we go back to the very same number. But there is in total 9 transitions. So because there is 9 transitions, there is no way that that you start at a point and you go. So you start at a vertex and you go back to the same vertex after an odd number of moves. So therefore, you have an odd number of total plus ones and minus ones. So therefore, one of them is odd, the other one is even, odd, even, or the other way around. So in that case, you are changing the sum of the exponents for that number and in its prime representation and prime factorization, I should say. And yeah, so that's it. That proves that squares won't work either. Okay, so squares squares don't work, basically. So far we have 2 negative answers. So squares don't work, but this is usually not the way to solve a problem, right? So far we know that n cannot be a prime power, a power of a prime, and similarly n cannot be a square. So n not equal to something square, m square. Where m is any integer. Obviously it can't be a prime because we already ruled that out. And then, then you start thinking that after, like I said, you play with this question with different examples, you realize that those are the only cases that seem not to work. You can play out the smaller cases starting with, and then going up to larger cases, you just realize that all the other cases work. So therefore, let's give an example, right? So let's consider a number which has 2 primes in it. Let's call it p and q, and they are raised to the powers a and b. And obviously, both a and b cannot be both even. So therefore, at least one of them is odd. Maybe both, right? At least one of a or b is odd. And this is a good news because that would tell us that the number itself has an even number of divisors, right? So the total number of divisors of n is, I think this is the proper way to use this notation, not to list them, but rather to count them. So number of divisors of n, positive divisors, integer divisors of n is a plus 1 times b plus 1. But because one of them is odd, it means that one of these factors, these 2 factors, is even. As a result, the number of divisors is even. And then, okay, so we now understand why odd doesn't work, but why should an even case work, right? So this is kind of an interesting problem. You can play with it, and eventually it's very easy to come up with a construction. The main idea is to think of it as a grid, all the divisors. So in total we have a plus 1 plus b plus 1. So we will create an a plus 1 by b plus 1 grid where the vertices represent the divisors themselves. An easy, quick way to do that would be to do the following. I can go ahead and create this a plus 1 by b plus 1 matrix. So a let's put the powers of p first. So 1, p square, and so on, all the way up to p to the power a. Similarly, 1, q, and so on, q square, all the way up to q to the power q to the power b. Now remember that one of a or b is odd, right? Suggesting that we have either an even number of rows or an even number of columns, right? So pretend that we have an even number of, say, columns. So maybe both of them are even, but at least one of them should be even, right? For this procedure that I'm about to show you to work. And all the inside these little squares, we are going to place all the divisors of our number, right? So that's a systematic way to make sure that we're not missing any of the divisors. So p squared, p to the power a. So q, p times q, p squared times q, and so on. P to the a times q, q squared, p times q squared, p squared times q squared, p to the a times q squared. Oh my god, this is torture. Okay, so one more. Q to the b, p times q to the b, p times q to the what am I doing? No, yeah, that's right. So p squared times q to the b, p to the a times q to the b. Awesome. So what I would recommend in general when I watch my videos again later on, I usually watch it in 1.5 times. So make sure from the settings you watch it fast, because I usually realize that I'm talking very slowly, and it can put you guys to sleep. So yeah, so better watch it fast. All right, so how can I place all these divisors on a circle, right? So placing them on a circle is just a fancy way of saying that you want to create a cycle, basically. So you have this grid. So how do you know that anytime you have a given grid, that you can create a cycle, right? So once you create the cycle, you should be done. Oh, obviously this can't be the case. So for instance, pretend we have a case like this, right? So with an even number of columns, we said. So how do I know that I can create a cycle? So once I have the cycle, I can just bend it into a circle, right? So what do you call it? Topology? Well, anyhow, so pretend one is here in that corner. So basically one idea is to just follow the vertices. So all of these are connected. And the nice thing about it is these are they are related to each other by 1 unit. Okay, so maybe I should have done that before I start so this is the one, but all of these vertices are the divisors of our number, pretend. And basically, yeah, so they are just different from each other by a factor of 1. So for instance, if your number is 2 squared times 3 cubed, this obviously works. What is this? 27 times 4, 54,108. Okay, so 1, 2 square here, and then you will go to the next one, 3 squared, 3 cubed here. So 2 times 3, 2 squared times 3, 2 times 3 squared, 2 times 2 squared times 3 squared, 2 times 3 cubed, 2 squared times 3 cubed, and so on. Okay, so how do we do that? The business, the labeling. So we can start from 1, and then we go this way, and then that way, that way. Hey, what is this business? What am I doing? I'm connecting each of them, right? So luckily, so all of these segments on this graph, this is a grid-looking graph, right? So the edges represent connections where the two vertices, which are the divisors, are related, prime related. And boom, so what did I do here? I created a cycle. So I was able to visit every single vertex on this graph, not every single edge, every single vertex. And if you guys remember, this would be a Hamiltonian path, or well, in that case, because I go back to 1, it's a cycle really, so it's a Hamiltonian cycle, not a how do you say that? Eulerian. It's not an Eulerian cycle. It's a Hamiltonian cycle. So the Hamiltonian cycle visits every single vertex once, and because you go back all the way to the beginning point, so you are allowed to visit the first vertex twice, but every other vertex has to be visited once only. And in the case of an Eulerian cycle, it is you visit every edge once. So this is not an Eulerian. So we are trying to find a Hamiltonian cycle. And well, it's clear that this thing will work. Why? Because one of the edges is let's do it, is an even number. So if you have the columns an even number, so what it will tell us is that, so when you start from a vertex, so you go down, go down, dot, 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 go down, and then you should go to the next one, and then go up, 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 and then stop there, and then go to the right. So eventually, because you have an even number, so the way it will work is you will come all the way, like you will do these things, and because you have an even number of column, oops, come on, okay, so 1, 2, 3, 4, 5, 6, so it will eventually go up, and then you will be able to connect it back, right? It doesn't matter, the number of rows in this case doesn't matter, right? So if it's odd or even, it doesn't affect it. It just affects the length of the thing, but it doesn't affect anything else. So therefore you will come from this direction and then go up, 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 and then da 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 da. So therefore the vertices here that's in my description are really the numbers themselves, and the relationship, the prime relatedness is the connections. So now that once you find this mapping, it's now easy to place the numbers on a circle, right? So therefore this tells you one-to-one, this is a bijection, there's a one-to-one relationship between okay, let's do it here. For instance, let me just do this example. So you just put your circle. So basically you can bend it topologically, so pretend this is a circle, right? So 1, so we go, so all I do is I just follow this Hamiltonian path, 2 square, what is this guy, 2 square times 3, 2 square times 3, and so on. So 2 times 3, 2 times 3 square, 2 square times 3 square, 2 square times 3 cubed, and so on. 2 times 3 cubed, 3 cubed, 3 squared, 3, and 1. Yep, we were able to put all the divisors along this circle. Okay, so are we done? No, not yet. Why not? Well, because we only proved it for numbers which have only 2 primes, and one of the primes have at least an odd exponent. What if we have 3 primes in the prime representation, right? So in the prime factorization of our number, how can we guarantee that this thing will go, right? So it will work. So then in that case, it's as if we are trying to find a Hamiltonian circle on the 3rd dimension, right? So it's as if once you finish one layer, you need to go up one layer and so on, and then you need to make sure that you can go back all the way back to the beginning point. So yeah, so if you're interested in this type of configuration, then you can go ahead and read some of the AOPS solutions, make use of that, these further dimensions. But instead, the in control is a pretty good idea of finishing the construction. There's only kind of like a gap in his logic, I think. I'm pretty sure, actually. And I want to elaborate on that, and then we can just finish it pretty quickly. So what happens if there is this 3rd guy, right? So you have a number, so p to the power a times q to the power b. Oops, come on. P to the power a, q to the, when I say the solution on AOPS, so it's on the AOPS contest page, right? So r to the power c. So all I know is not all of them are even, at least one of them is odd, right? So whichever one is odd, so suppose that, I don't know, suppose that b is the odd one. Well, if the others are odd as well, so fine, but at least one of them has got to be odd. So then you can inductively do the following. So you can, starting from you can list all the remaining ones, and starting from the leftmost one, you can combine them. So we already know that you can do q to the p to the a times q to the b, right? Why? Because b is odd. Now we will just check how we can add the 3rd one, r to the c, as well. But the first one has to be doable. So you can't have, for instance, if a and c are even and b is odd, obviously you cannot start with pa times rc, because both a and c are even and there is no Hamiltonian path for this number. So you should start with, and this is the part which is missing in the proof of in control on AOPS. So therefore, yeah. So once you have this starting point, so how can you add all these new divisors? So far our number had a plus 1 times b plus 1 divisors, a plus 1 times b plus 1 divisors, and we know that we can put them in a circle. So you can put them in a circle, or let's just say a Hamiltonian path exists. Hamiltonian cycle, sorry. Cycle exists. Cycle in the sense that you go back to the same starting point. So how can you guarantee that when you further multiply this whole thing by c plus 1, you can still have a Hamiltonian cycle? Well, it's quite easy actually. You just have your initial thing. And remember how your initial thing was. So P is on one side, Q is on the other. So we already know that we can construct this, right? So you have a certain power of P, or maybe a multiple with P and Q, whatever, alpha, beta, let's say. And then, so all of these are here. So already you have a construction for P to the A times Q to the B. So all I now need is to add the remaining ones related to C onto this picture, and it's quite easy. So all you do is so you start with each and every single gap. You add so in total we have a plus 1 times b plus 1 gaps, and into each gap I'm going to add c plus 1 divisors. So how do you add them? And it doesn't matter if if c plus 1 is odd or even. So all you do is, starting with the one closest to 1, so you keep adding powers of r. So I'm going to add r here, r square, and so on, all the way up to here. I keep going. Wait a second. Wait. I just did a small typo. Okay, hold on. So let me do the following way. So I need more space basically. Okay, there you go. Okay, so 1, P, the first prime, and on the right hand side you have also a bunch of primes. Okay, so but we know for sure that Q is the other one. Okay, so we start from 1, so we can add R next to it because R itself is a prime, R square, all the way up to R to the power C. And then I introduce P times R to the power C. Okay, obviously this is a divisor as well. Do you guys see how I add a P here? And then we reduce the powers of R to the C. So this guy would be P times R to the C minus 1, and so on. All the way up to the next one. The one next to it would be P times R. And then finally you reach your P. So the next prime in line would be, so if the next divisor in line is D, right, so which is obviously either P square or it is P times Q. Okay, it doesn't matter. I just leave it blank. I don't place anything new here. But between D and the next guy, let's call it D prime, what I do is I do the same trick that I did earlier. So I add here D times R, and then D times R square, and so on. I rise all the way up to D times R to the power C, and then I introduce the next prime. Yes. So D prime R to the C. Because remember early on, D prime and D, they are prime related when you have two primes in the prime factorization. So therefore, either D prime is a multiple of D, or D is a multiple of D prime. So in that case, so when you take the ratio of these two numbers, the RC's will cancel, and then D prime to D, yeah, that works. So therefore, the next one would be D prime times R to the power C minus 1, and you go down. Ooh, okay, so, all right, so now it makes sense. So you put a bunch of numbers, then you leave a blank. Then you put a bunch of number between the next consecutive pair, and then you leave blank. And then you put your, all these R to the C related divisors, and then you leave a blank, nothing here. You put them and then leave a blank, put them. So because we have an even number of divisors in the P to the A times Q to the B, because we assumed that we start always as the basis step, we start with the one which have an odd power at least, right? So therefore we would have an even number of gaps here in this construction, and every other gap we place the divisors in a careful way such that they are prime related between the, and so therefore this way we are able to make use of all of them, right? So therefore this one will be blank, there will be nothing here. So in the one before that, so if this divisor is, I don't know, d double prime, so we will be putting all of them related to d double prime, right? So we will start with d double prime times r, and then d double prime r square, all the way up to d double prime r to the power c. And then when we pass to the next level, it will be q times r to the c, right? And obviously d double prime and q, they are related. What do you call it? Prime related. So therefore now I can reduce it again, q times r to the c minus 1, and all the way up to q times r, and that's it. Now we've made use of all of them. So this construction, you can inductively now continue adding new stuff into it, right? So you can now go ahead and add the fourth guy, and so on. But notice that in each construction you have an even number of gaps, prime related, like adjacent vertices along the circle. So within one gap you make the construction, within the next you leave it blank, and so on, and then you complete the circle, and that's it. All right, so that basically solves the problem. So the final answer is to this pretty nice problem. I think I kind of messed it up in my explanation, like but the idea is there, so you can work on this problem, and it's a pretty nice problem. I really enjoyed it the first time I read the problem. Usually the TSTs or TSTSTs are pretty nice. I usually try to look at the Canada Math Olympiad problems, and obviously IMOs and shortlisted problems are always there. So but yeah, so therefore going back to this problem, the answer therefore is this construction is possible. You can put all the divisors of a number n inside on a circle such that two adjacent entries are prime related, as long as our number n is not a power of a prime number, or it is not a perfect square. As long as it's not one of the two, then it's possible to place all of these along this circle. So it has a nice blend of number theories, a little bit graph theory in this whole construction, and it's kind of enjoyable, and a little bit combo even, right? So we're counting the number of divisors and so on. So I don't know how we would classify this problem, right? So it's a mix between these concepts, probably. Yeah, I think it's a combo problem, right? But anyhow, okay, so hope you enjoyed it, and looking forward to see you guys in our next lecture.